Welcome to the first part of the ARSET training, Mapping Crops and Their Biophysical Characteristics with Polarimetric Synthetic Aperture Radar and Optical Remote Sensing. My name is Sean McCartney, and I'm joined today by my colleague Sarah Banks from Environment and Climate Change Canada and Laura Dingle Robertson from Agriculture and Agri-Food Canada. This four-part advanced training builds on the previous ARSET agricultural training held in October of 2021. For those unfamiliar with the Applied Remote Sensing Training Program, or ARSET, ARSET is part of NASA's Applied Sciences Capacity Building Program. ARSET provides accessible, relevant, and cost-free training on remote sensing satellites, sensors, methods, tools, and applications. Trainings are offered online and in person for beginners and advanced practitioners alike. Though unfortunately, due to the COVID-19 pandemic, the program has suspended in-person training. Trainings cover a range of data sets and analysis tools and their applications to air quality, agriculture, disasters, land, and water resources management. ARSET's goal is to increase the use of earth science remote sensing and model data in decision-making through training for professionals in the public and private sector, environmental managers, policymakers. Trainings are freely available to anyone with an internet connection and conducted either live, instructor-led, or self-guided, such as our Fundamental to Remote Sensing. Since 2009, the program has reached over 50,000 participants from over 170 countries. All ARSET materials are freely available to use and adapt for your curriculum. If you use the methods and data presented in ARSET trainings, please acknowledge the NASA Applied Remote Sensing Training Program. Over these 4 weeks, there will be 4 2.5-hour sessions, which will include presentations, case studies, and question and answer sessions. The same content will be presented at 2 different times each day. Session A will be presented in English, and Session B will be presented in Spanish. All materials and recordings from each session will be available from the training webpage provided by the link on this slide. There will be one homework assignment for all 4 parts of the training. Answers must be submitted via Google Form, which can be accessed from the training page on the ARSET website. Homework will be made available on May 3rd with a due date of May 17th. A certificate of completion will be awarded to those who attend all live webinars and complete the homework assignment by the deadline. You will receive a certificate approximately 2 months after the completion of the course from Marinas Martin. The prerequisites for this 4-part training are ARSET's Fundamentals of Remote Sensing, Session 1, Introduction to Synthetic Aperture Radar, and Agricultural Crop Classification with Synthetic Aperture Radar and Optical Remote Sensing. Links to each of these trainings are provided, and we encourage you to go through them to familiarize yourselves with content directly related to this training. This slide outlines what each part of the 4-part training will cover from April 12th through May 1st. We hope you would join us for all 4 parts to gain as much value from the training as possible. If you are not able to attend one or more parts, a recording will be made available within 48 hours of the training day on the ARSET website. Regarding training objectives for this webinar series, by the end of this training, attendees will be able to explain the theory behind SAR polarimetry, especially as related to crop characteristics. Attendees will be able to generate polarimetric parameters using open source imagery and software and perform a time series analysis of crop growth. Identify how SEN4STAT can support national statistical offices in the uptake of satellite Earth observations for agricultural statistics, And finally, perform a time series analysis of crop types using Sentinel-2 derived leaf area index. I will now hand it over to Sarah Banks from Environment and Climate Change Canada to provide the theoretical background using SAR Polarimetry for agriculture. Sarah, over to you.
Hello everyone, my name is Sarah Banks. I'm a physical scientist with Environment and Climate Change Canada and a PhD student in the Department of Geography and Environmental Studies at Carleton University in Ottawa, Canada. Today I will be presenting the first of 4 sessions on mapping crops and their biophysical characteristics with synthetic aperture radar and optical remote sensing. In this lecture, I will focus on the theory of SAR Polarimetry. Over the course of this lecture, we will cover 4 main topics. We'll start with a very short review of electromagnetic radiation, followed by a discussion of the system characteristics that define a SAR sensor. We will then go over some common SAR imaging modes and finally talk about polarimetry. Now, to fully grasp the contents of this lecture, it is strongly recommended that you review the prerequisite material shown on the right-hand side of the screen. From the prerequisite material, you will recall that electromagnetic radiation is commonly conceptualized as behaving like a wave, and there are different ways that these waves can be described mathematically. For simplicity, we typically base their profile on sine or cosine curves, which are just mathematical functions or mathematical curves that are useful for modeling periodic or cyclical phenomena. And it is convention to represent these curves on a right-handed Cartesian coordinate system, with the z-axis indicating the direction of travel. The x and y planes are then defined at the sensor, with convention also being that the x-axis is parallel to the Earth's surface. Now that I've reminded you all of what electromagnetic radiation is, we can get into an important system property of SAR sensors, which is their polarization. Now, you've likely seen a figure like this before, with the blue line used to represent the electric field of an electromagnetic wave, and most of the time it is oscillating in the vertical direction. But the electric field of an electromagnetic wave can actually oscillate in any direction. In this example, you can see that the electric field is oscillating horizontally. But again, this can be at any angle perpendicular to the direction of travel. And the reason why this is important to know is because polarization describes the orientation and shape that's traced by the wave's electric field. So why is this important? Well, radars only transmit and receive microwaves of a specific polarization. Here, for example, we can see that this radar antenna can only transmit and receive vertically polarized microwaves. Now, it's also important to know that electromagnetic radiation can also be completely unpolarized or only partially polarized. Light that is emitted by the sun, for example, shown here in black and gray, is an example of completely unpolarized electromagnetic radiation. Whereas what is transmitted by a SAR sensor is completely polarized, and we have an example of that shown in blue. So there can be varying degrees of regularity to the electric field vector waveform. When completely unpolarized, the electric field oscillates randomly. And when completely polarized, oscillation is in the plane of polarization at all times. And when there is partial polarization, there's a combination of both. Again, for a SAR sensor, though, the transmitted signal is always polarized, though what is received following interaction with the surface or a target is either partially or completely unpolarized most of the time. And we can quantify the degree of polarization, which is the ratio of the polarized power to the total power. Most radars today transmit and receive horizontally polarized or vertically polarized microwaves. Regardless of what is transmitted, though, the backscattered wave can have a variety of polarizations, and it is the analysis of these different transmit-receive polarization combinations that is the focus of radar polarimetry. Now that we know a bit more about polarization, we can talk about phase and polarization together, which is really important for understanding radar polarimetry. Before we begin to talk about phase, though, I wanted to start by describing what a vector is, because we use this term and conceptualization a lot in radar polarimetry. So you can think of a vector as a quantity with both direction and magnitude. Typically, vectors are represented as arrows, with the head at some point and the tail at the origin, or using an ordered list of numbers. We can denote a vector using bold-faced text, or sometimes using an arrow over the number. If you have a vector and want to refer only to its magnitude, though, you can use two vertical bars as shown here. And an example of a vector you all may be familiar with is velocity, which is just speed in a given direction. You can represent vectors on a Cartesian coordinate system, and it is worth noting that we can use the same notation for a vector and point, because you can essentially think of a point as being a vector with its tail at the origin of the coordinate system where the x and y axes cross. In linear algebra, which is something that we use in radar polarimetry, the tail is usually at the origin where the x and y axes cross as well. When we use a list of ordered numbers to represent a vector, essentially this list tells us how to go from the tail, or origin, to the head, and it is convention to write this list vertically using square brackets. One of the reasons why we use vectors is that it's easier to manipulate coordinates than direction and magnitude. Here I'm also showing how we can determine the magnitude of the vector, which is equal to its length. To do this, we simply use Pythagorean theorem, which states that the square length of the hypotenuse of a right-angled triangle is the sum of the squares of the lengths of the other two sides. So to get the magnitude of the vector shown here, we simply take the square root of 2 squared plus 3 squared. Vectors can also be added together really easily. Here I'm showing you two different vectors, A and B, and adding these is really just the equivalent of translating B's tail to the head of A. Then the new vector, represented by C, is the direct line segment from the tail of A to the head of B. And what's really interesting is that the order of addition doesn't matter. A plus B is equivalent to B plus A. Again, you can think of it like a list of directions. Here I'm showing you the addition of vectors A and B using a list of values. In this case, we can think of it like walking along the x direction by 5, moving up along the y direction by 5, then along the x direction by 2, and down in the y direction by 2, which is again equivalent to drawing a line from the tail of A to the head of B. And if we know how to add vectors, this can be really useful for visualizing something called interference, which is when waves occupy the same space or move simultaneously through the same medium. And depending on differences in their phase, which we'll talk about shortly, we can have either constructive or destructive interference. So what I'm showing you here is multiple different vectors, each of which represents a different wave, which you can think of as occupying the same space at the same time. And the product of all these waves is simply the sum of all of their amplitudes and phases together, which I'm showing you here as the final vector in purple. So now that we know what vectors are, we can talk about phase, which is really important in SAR polarimetry. To start, there's really this interesting relationship between sine waves and circles. I have a short video clip which shows a vector rotating in an anti-clockwise direction about a fixed point. Now, the length of this vector remains the same, but the distance between the head of this vector and the horizontal axis changes through time. And if we map these changes in distance through space, we can see that a sine wave is formed as that vector makes a full 360-degree rotation. Now remember that these waves model repeating cyclical phenomena, so you can think about waves in terms of cycles, with a beginning, middle, and end, after which the same shape repeats. With this in mind, you can see that we can use the relationship between circles and sine waves to measure phase, or the stage of the wave cycle. And because one complete rotation of that vector draws out the equivalent of one complete wave cycle, we can express phase in degrees, which simply measures the angle made between the vector used to represent the wave and the horizontal x-axis as shown, and which we represent using the Greek letter phi. So 1/4 of a wave cycle can be represented by a rotation of 90 degrees. Half a wave cycle can be represented by rotation of 180 degrees. 3/4 of a wave cycle by 270 degrees, and a full wave cycle by 360 degrees. And remember that the length of the vector represents the wave amplitude. So with the vector, we know both the wave amplitude and its phase. And at different stages in the wave cycle, we can see how a wave's amplitude changes by projecting the length of this vector onto the y-axis. So how is this information useful? Well, it's important to first know the initial phase, or the stage at which the wave cycle begins. But with that, we can start to look at differences in phase between different waves. Phase differences measure the offset in space or time of one wave with respect to another. Waves can be said to be in phase if their origins of phase 0 degrees are perfectly aligned. When this is not met, though, waves are said to be out of phase. In this example below, I'm showing you two waves which happen to have the same amplitudes but are out of phase. And in this example, I'm showing you two waves that happen to be in phase but with different amplitudes. And finally, in this example, we have three waves with equal amplitudes, two of which are in phase and another that is phase shifted by 180 degrees. Phase is also useful for characterizing polarization, which we'll talk about later, and is key to interferometric SAR, which uses differences in phase to measure changes in the position of targets. Phase is also impacted by the structure of a target, so by looking at differences in phase, it can help us distinguish between them. Despite the fact that phase information can be very useful, it's not always available or calibrated. Two common types of data you will encounter are single-look complex products, where phase is available. This includes RadarSat-2 fine wide quad-pol mode data and raw SLC Sentinel-1 data. There's also ground range detected products where phase information is not available. And an example of this includes the Sentinel-1 GRD products available on Google Earth Engine. So each wave has a phase angle describing at what stage in its wave cycle it's in, as well as an amplitude, which is related to its power. Within this context, we can use something called complex numbers to store both values. So you can think of this as just another way that we can describe waves mathematically. So every complex number has both a real value and imaginary value, expressed using the following equation, where x and y are real numbers, and I is what's called the imaginary unit, or the number whose square is equal to -1. Sometimes the symbol J is used instead of I, which is more often the case in electrical engineering, while I is more common in physics and math. And the reason why it's called the imaginary number is because I is not defined. You just have to imagine what it is. Here in the figure below, you can see that we have just replaced the x and y axes from our previous examples with what are called the real and imaginary dimensions. With this, we have one complex number with a real value in the real dimension and a value in the imaginary dimension as well. So imagine again that this point is actually a vector, then the phase is represented by the angle this vector makes with the real dimension, measured in the anti-clockwise direction, and its magnitude is equal to its length. Now, if that sounds a bit confusing, you can just think of complex numbers as a construct. A construct just like negative numbers, which didn't always exist either. In fact, we can compare complex and negative numbers to make them easier to understand. For example, a negative number might seem strange because how can you have less than nothing? Well, a complex number is also strange because how can you take the square root of less than nothing? For both, though, there are intuitive meanings. For negative numbers, you can consider that they mean the opposite, and for complex numbers, the intuitive meaning is rotation. If we think about their use in coordinate systems, negative numbers are used to move backward from the origin, and complex numbers can be used to effectively rotate about the origin. So if you think of each complex number as a vector with the tail tied to where the imaginary and real axes cross, then the phase is the angle made between the horizontal or real dimension and the vector in the anti-clockwise direction, with values ranging from 0 to 360 degrees. And the total wave amplitude is the length of this vector. But you'll oftentimes see this value expressed in linear power, which is equal to the amplitude squared. To get that value, you again use Pythagorean theorem. You take the magnitude in the real direction A, square it, then take the magnitude in the imaginary direction B, square it, add those together to get the length of Z squared, which is the amplitude. Now that we know about phase, we can talk a bit more in depth about polarization. Again, polarization describes the orientation and shape traced by the wave's electric field, and it is convention to consider the shape traced by the tip of that rotating vector projected onto a plane or flat surface. So in this example, I'm showing you a wave with an electric field oscillating in the vertical direction. The blue line represents the path traced by the tip of the electric field vector through space and time. Now let's imagine that this path, that blue line, is a solid object. If we were to shine a light behind it, then project that shape onto a plane, it would just be one vertical line. And this is what we call linear vertical polarization. Now imagine that the electric field vector is just oscillating in the horizontal direction parallel to the x-axis. The red line again really represents the path traced by the tip of the electric field vector through space and time. Now again, let's imagine that this path, this red line, is a solid object. If we were to shine a light behind it, then the shape the object would project onto this flat surface would just be a horizontal line. And this is what we call linear horizontal polarization. Linear vertical and linear horizontal are the two most important polarizations because most radars transmit and receive linear horizontal and linear vertical. Now, the linear refers to the fact that a straight line is being traced by the tip of the electric field vector, and horizontal and vertical refers to the fact that oscillations are along the x and y axes respectively. But again, it's important to remember that the electric field can oscillate at any angle, and in fact, we can measure what's called the wave's orientation angle, which is simply the angle made between the wave and the horizontal x-axis, shown here and measured in an anti-clockwise direction. Values therefore range from 0 to 180 degrees and are represented using the Greek letter psi. And now what I'm showing you are just some different orientation angles you can have. But again, two very important orientation angles to remember are linear horizontal at 0 degrees and linear vertical at 90 degrees. Up until this point, though, we have only seen linearly polarized waves, but that's only one of three different canonical polarization states. So in addition to linear, there's also elliptical and circular polarization. Before we dive into those, though, what's interesting is that we can describe the polarization state of any wave by fitting two orthogonal waves to the total wave cycle. By convention, we use one along the vertical and one along the horizontal axis. And this might sound a little bit confusing, but let's see how it works for circularly polarized waves. For circular polarization, you can think of it as the superposition of two linear orthogonal waves that are 90 degrees out of phase and have equal amplitudes. And superposition really just describes the behavior of waves that occupy the same space and time as they travel through a medium. Now, in this example, what I'm showing you is a linear vertical polarized wave in blue. And we know that the shape traced by the tip of that electric field vector will just be a vertical line. We also have a linear horizontal wave on the right-hand side shown in green, and we know that the shape traced by the tip of that electric field vector will just be a horizontal line. Now, both waves have equal amplitudes, and they are 90 degrees out of phase. So to get circular polarization, we're just going to superimpose them or make them occupy the same space at the same time. But how does this make a circular shape when we project this onto a plane? To visualize this, let's say that this house is our target, and you can think about the difference in arrival time to the target for each part of the wave. And I want you to focus on when each wave reaches its maximum amplitude. If I look at the green wave, it arrives first. It reaches its maximum amplitude at the house first. The second component to arrive would be the vertical, followed by the other horizontal component, and then the other vertical component. So if we take all those together, the shape that's being traced out in time is actually a circle. Now this animation is showing you what I was just describing, and the red line is what you should be focusing on, which is the tip of the rotating electric field vector, and it's tracing a circle through space and time. So now that we have a good understanding of what linear and circular polarization is, let's talk about elliptical polarization. Now, it's important to know about elliptical polarization because this is the typical polarization state of what is backscattered by the surface. Linear and circular polarization can therefore be thought of as special cases, and this is typically the polarization that SAR sensors transmit. So elliptical polarization can be described in a similar way to circular polarization. You can think of it as the superposition of two linear orthogonal waves, though in the case of elliptical polarization, they are not 90 degrees out of phase, and or they do not have the same amplitudes. So in this example, we again describe the full wave cycle by fitting one vertical and one horizontal wave, and the shape being traced out through space and time by the tip of the electric field vector is an ellipse. And again, it's possible to describe any wave using just two orthogonal components, usually one oriented along the horizontal axis and the other oriented along the vertical axis. And it's possible to characterize the degree of non-circularity of a wave using something called the ellipticity or eccentricity. And that's just a function of the semi-major and semi-minor axes A and B shown here, and which is represented by the Greek letter chi. Values are measured in degrees and range from the positive to negative 45. So in this example, I'm showing you a wave with an ellipticity of 34 degrees. But let's look at how that can change depending on the relative size difference of the vertical and horizontal components. So a wave will tend toward the horizontal as the vertical component tends to 0 and vice versa. So let's see what happens if this wave tends more to the horizontal. We can see that the vertical component starts to decrease. And again, any polarization state can be described by two linear orthogonal waves as long as the phase is also measured. So what's interesting is that if our SAR sensor can measure just two orthogonal components, we can measure circular, linear, and/or elliptical polarization. Now we can combine both the ellipticity and orientation angle. In the first example, the orientation angle of this wave is 45 degrees, measured again from the positive x-axis in the anti-clockwise direction, though the ellipticity here is 0. In the middle, we have a wave with the same orientation angle, 45 degrees, but an ellipticity of 34 degrees. Now for the circular polarization on the right, again we have an ellipticity of 45 degrees, but we do not define its orientation angle. But as we saw, chi values can be negative. Let's look at why. Both elliptically and circularly polarized waves have a handedness or a direction of rotation, which just tells us if the vector tip is rotating clockwise or anti-clockwise. In this example, we have the viewer located at the source of the wave looking toward the direction of travel. The example closest to the viewer shows a wave spinning in the anti-clockwise or left-handed direction, while the one farthest from the viewer shows a wave spinning in the opposite direction or clockwise direction. In the example on the left, in the example of the left-handed rotation, chi values would be negative, and in the right-handed rotation, chi values would be positive. But when you view these same waves from the target toward the source, both waves would be rotating in the opposite direction. So it's really important to understand that the direction of rotation depends on where you are viewing the wave from. There are two different conventions that are used that you should be familiar with. In all cases, we define a coordinate system by 3 axes, though we have something called the forward scatter alignment convention, where the positive z-axis always points in the direction of travel. And we have the back scatter alignment convention, where the positive z-axis always points towards the target. Now, the backscatter alignment convention is more commonly used, but it's important to know that both do exist. Remember, though, that waves can be completely unpolarized, which is when the electric field vector oscillates randomly, and there is no clearly defined polarization. There are also completely polarized waves, where these oscillations are in the plane of polarization at all times. And then you can have waves that are partially polarized, which is really the superposition of many different polarizations with one or more being dominant. Now, the wave that's transmitted to the target is always fully polarized, but what we get back from the target depends on the characteristics of it. We can define two different types of targets, coherent and incoherent. Backscatter from a coherent target is completely polarized, and examples include things like buildings. On the other hand, backscatter from incoherent targets can be partially or completely unpolarized. Most natural surfaces fall into this category and includes things like trees, which are made up of multiple randomly oriented elements like leaves, needles, trunks, and stalks, resulting in multiple waves that are scattered from all these that vary in phase and amplitude or power. Again, the backscattered wave is a superposition of all these waves, and we can define the degree of polarization as the ratio of the polarized power to the total received power. So now we'll talk about some common SAR imaging modes. As we've mentioned, SAR sensors are designed not only to transmit microwaves of a specific polarization, but to also receive a specific polarization only. So it's necessary not only to define the polarization of the transmitted wave, but also the polarization that's received. To do this, we use a combination of two letters. The first always indicates what polarization was transmitted, and the second always indicates what polarization was received. Again, the most common transmit-receive polarizations are some combination of linear horizontal, represented by H, and linear vertical, represented by V. So again, what I'm showing you here is the first letter indicating the transmit polarization, and the second letter indicating the receive polarization. Now, what is transmitted by the sensor is very closely controlled. So the wave that arrives at the target is fully polarized, say in the linear vertical or linear horizontal. But just because that's what's transmitted doesn't mean that's all that we will receive. Remember that linear and circular polarization are special cases, and that most often waves are elliptically polarized, meaning that they have both a vertical and horizontal component that are not 90 degrees out of phase and or differ in amplitude. And remember that we can describe any electromagnetic wave using a linear horizontal and linear vertical wave fitted to the entire wave cycle. So now what I'm showing you is the transmission in the linear vertical. And what is backscattered is elliptically polarized, meaning that it contains both a vertical and horizontal component. But because our polarization is also vertical on receive, the polarization is VV, we can only receive the vertically polarized component. And that's also true if we transmit in the H and receive in the H. So what I'm showing you here now is our sensor transmitting linear horizontal, and then just receiving that which is also linearly horizontal polarization. There is some vertical component, but we can only receive the linear horizontal because our receive polarization is linear horizontal. Now, all other factors being equal, returns for a given polarization depend on the amount of energy that hits the target. So it's proportional to the target cross-section. In other words, the size and orientation of the target and the polarization of what is transmitted determines the amount of energy that's returned. Now, what I'm showing you here are the returns for both linear horizontal and linear vertical from a given target shown in gray. Now, as I rotate that target towards the horizontal plane, we can see that our returns in the vertical start to decrease. And as we continue this rotation, and the target becomes more horizontally oriented, returns in the HH polarization increase while returns in the VV polarization decrease. So when you transmit and receive the same polarization, it's referred to as co-polarization. But it's also possible to transmit one polarization and receive another. We call this cross-polarization, and in this example, what I'm showing you is VH, where we transmit in the linear vertical, and noting again that just because we transmit linear vertical doesn't mean that that's all that is scattered back towards the sensor. But in this case, we're just going to be receiving in the linear horizontal. So when incident microwaves encounter a rough surface, returns are mostly in the same polarization as what was transmitted. However, when scattering is within a volume or medium, such as when incident microwaves encounter a vegetated canopy, something called volume scattering occurs, where incident microwaves interact with varying elements within the canopy. And this generally results in higher cross-pol returns, so higher HV or VH. So with linear horizontal and linear vertical, there are 4 possible transmit-receive combinations. We can have HH, where we transmit in the linear horizontal and receive in the linear horizontal. HV, where we transmit in the linear horizontal and receive in the linear vertical. VH, where we transmit in the linear vertical and receive in the linear horizontal. And VV, where we transmit and receive in the linear vertical. With just one polarization, though, this really only provides sort of one-dimensional information about the surface or target. So with just one polarization, we can really only talk about varying degrees of brightness. And while that can be useful for distinguishing certain targets, it can also be advantageous to collect more than one polarization. So in fact, some SAR sensors are dual polarized, and some of those also record the phase difference between different polarizations. And these are called coherent dual pol radars. For those that only record intensity information, though, we call those standard dual pol SARs. So there are only 3 combinations possible with dual polarized SAR sensors, including HH and HV, where linear horizontal is transmitted and both linear horizontal and linear vertical are received. There is also VV and VH, where linear vertical is transmitted and both linear horizontal and linear vertical are received. And then we have HH and VV, where both linear horizontal and linear vertical are transmitted and both are also received. Now the co-pol phase difference, which measures the phase difference between HH and VV, can be really useful for characterizing the structure of targets, as values are indicative of the number of bounces incident microwaves experience before returning to the sensor. When the phase difference is 0, we can interpret this as an odd number of bounces, and this is characteristic of scattering from a rough surface. A phase difference of 180 degrees can be interpreted as an even number of bounces and is characteristic of scattering from 2 perpendicular surfaces, which is called double bounce scattering. And values between these 2 extremes are then interpreted as indicative of volume scattering. So every time there's a surface interaction, HH and VV go in and out of phase. When there's an odd number, HH and VV are in phase, and when there is an even number, HH and VV are out of phase. There is also a cross-pol phase difference, but it's usually quite random. There's also a quad-pol or polarimetric radar, which is the equivalent of transmitting and receiving all single polarizations and also recording the phase differences between them. Polarimetric or quad-pol radar requires the transmission and reception of two orthogonal polarizations, which are typically linear horizontal and linear vertical. And to do this, a switch directs energy to the horizontal and vertical parts of the antenna in sequence, and the horizontal and vertical are received simultaneously. And for this to be fully polarimetric, the relative phase differences are also recorded. So again, this is equivalent of capturing all four single polarizations together, as well as their relative phases. And so one of the advantages of collecting quad-pol or fully polarimetric data is that you have the information available to characterize so-called scattering mechanisms, which help us identify targets and or surface types, as well as monitor changes in what we call scattering behavior through time. And these are roughly categorized as rough surface scattering, which is characteristic of rough surfaces, volume scattering, which is typically observed for vegetated surfaces, and double bounce scattering, which we often see for buildings. So the main benefit of fully polarimetric radar is that they can capture complete scattering characteristics, including target orientation. And we can do something called polarization synthesis, which allows us to simulate the transmission and reception of any polarization combination, even though we just transmit and receive linear horizontal and linear vertical, which can help improve the detectability of targets and or the contrast between them. Some of the cons of fully polarimetric radar are, though, that it requires 2 times the pulse repetition frequency or data rate and power usage of a dual polarized SAR. And the available power and data rate are extremely limited for spaceborne platforms. So to keep the power usage constant, the swath is often half that of dual pol data. An alternative to fully polarimetric or quad-pol radar is something called compact pol, which is when one polarization is transmitted and 2 orthogonal polarizations and their relative phase are received. And really the main benefit is that these systems operate at half the pulse repetition frequency of fully polarimetric radars, which allows them to acquire images over very large swaths. Now this can be implemented in a number of different ways, though the preferred way is to transmit a circularly polarized wave and then receive both in the linear horizontal and linear vertical. And there are several satellites with the compact pol option, including ALOS-2 RISAT-1, SAOCOM, the RadarSat Constellation mission, and NISAR. So in this figure, I'm just showing you a visualization of this transmission in the right-hand circular and receiving both linear horizontal and linear vertical simultaneously, as well as their relative phase. So with all this information, we can finally talk about polarimetry, which is the science of acquiring, processing, and analyzing the polarization state of an electromagnetic field. So essentially what we transmit is a fully polarized wave. There's an interaction between the target and that wave. And then we receive typically multiple waves of varying amplitudes and phases, which are partially or completely unpolarized most often. And so in radar polarimetry, we study why and how these differences arise based on the characteristics of the surface, including roughness, orientation, and shape. So for this part of the lecture, we're going to be going over three different things. We will start with a review of what vectors and matrices are, and then we'll talk about commonly used vectors and matrices in SAR Polarimetry, and then we'll talk about decomposition. Before we go any deeper into polarimetry, it's important not only to know about vectors, but also about matrices. So let's do a quick review of what a matrix is and have a short introduction on matrix algebra. A matrix is really just an array of numbers arranged in m number of rows and n number of columns. And we use these a lot in radar polarimetry, both to store and transform our data. A vector can also be considered a matrix with one row or one column. By default, though, we use the column form. And the dimensions of the matrix are given in terms of m number of rows and n number of columns. When referring to a specific element of a matrix, we identify the row and then the column. In this example, we're looking for element 1, 2, shown in red. That would be the first row, second column. In the second example shown in green, we're looking for the element stored in the first row and third column. And in the example shown in blue, we're looking for the element stored in the second row, third column. So let's look at the differences between vectors and matrices. A vector is just an ordered list of numbers with one row or one column, and a matrix is an array of numbers of one or more rows and columns. By storing our data in a matrix format, we can apply a lot of interesting transformations. We can add and subtract values and multiply them. And another useful thing we can do is transpose our matrix, which is just mirroring the matrix along the main diagonal. In this example, we're transposing matrix A, and we use the superscript T to remind ourselves that the matrix has been transposed. If we want to add and subtract matrices, we just add and subtract elements that are in the same position. And this means that in order to add and subtract matrices, they have to have the same dimension. So in this example, we're adding matrix A to matrix B, and we simply just add all the elements that are in the same position to form the final matrix C shown in purple. And I won't go into the same amount of detail here, but it's the same process if we want to subtract matrices. Multiplying matrices is more complicated though. Here we will show you an example of how to multiply matrices, but it's worth noting that this is a construct. This was something that was invented. It could have been done a number of different ways, but this is the way that's been defined. So let's say that we have two different matrices, A and B. Well, we can only multiply them if the number of columns of A is equal to the number of rows of B. So in this example, both matrices are 2 by 2. So a simple trick to tell if they can be multiplied is to list the size of both matrices and look at the two numbers closest together. If these are the same, then those two matrices can be multiplied. And it's also important to note that the order of multiplication matters. So how do we do this? Let's first look at the top left entry. This is the product of the first row with the first column. The top right entry is the product of the first row with the second column. The bottom left entry is the product of the second row with the first column. And the bottom right entry is the product of the second row with the second column. So now let's talk about some different ways we can characterize our data using some common vectors and matrices. As we saw previously, the wave vector is the simplest way to describe wave polarization mathematically, but it's also not always the most practical. So something that was introduced is called the Stokes vectors, which fully describe both fully and partially polarized waves. And to make things easier, they're usually stored as a vector. You'll sometimes see these represented using I, Q, U, and V, or using some combination of S and 4 subscripts, sometimes starting at 0 or 1. For now, we're going to stick to the I, Q, U, and V convention. So you can imagine that for a single pixel, you have these 4 different values stored in 4 different image bands, and that would be one way to represent your data for every pixel within your image. The first element, I, is simply equal to the total wave power or intensity. And remember that the total power or intensity is the total amount of energy in the wave, which is equal to the amplitude squared. Now you may be wondering why we square the amplitudes. It's because we are just interested in this length here. And you'll remember that the length of c squared is simply the sum of the length of b squared plus the length of a squared. And the brackets used in this equation indicates that averaging was applied over time, which is necessary when waves are partially polarized. Note that this first parameter does not contain any polarization information. It's just the total power or intensity of the wave. And if we wanted to calculate the amplitude, we would simply take the square root of the sum of each magnitude in the horizontal and vertical direction. Q is the second Stokes parameter, and it's useful if we want to know how linearly polarized the wave is. So what we do is just take the difference between the horizontal and vertical components, and this just tells us the extent to which the wave is vertically or horizontally oriented. When values for Q are greater than 0, this indicates more vertical orientation, and when values are less than 0, it indicates more horizontal orientation. Now, we need an additional term U because if waves were oriented at the positive 45 or at negative 45 degrees, they would still be linearly polarized, but Q would be equal to 0. So U tells us the extent to which the wave is polarized at the positive or negative 45. When U is greater than 0, it's more oriented in the positive 45 direction, and when it's less than 0, it's more negative 45. The final parameter tells us about the handedness of the rotation. So whether it's rotating in the clockwise or right-handed direction, or in the anti-clockwise or left-handed direction. When values are greater than 0, that means it's rotating in the left-handed direction, and when it's less than 0, it's rotating in the right-handed direction. And all these parameters together can provide a clear picture of both the intensity and polarization state of the wave. For waves that are completely polarized, we don't have any value for Q, U, and V because these describe the polarization state of the wave. But we do have intensity, and there are equal parts in the horizontal and vertical dimension because the electric field vector is just rotating randomly in all directions. So both are actually equal. For a linearly polarized wave, we have a positive value for both I and Q, whereas U and V are equal to 0. For a linearly polarized wave at the negative 45, we have a positive value for I, Q is equal to 0, U is negative, and V is also 0. And for a right-hand circular polarization, we have a positive value for I, U and Q are equal to 0, and V is positive, indicating a right-hand circular orientation. And the Stokes parameters together can also measure the degree of polarization, which is just the ratio of the polarized power to the total power. So we take the square root and sum of Q, U, and V and divide by the total power. When m is equal to 1, that indicates that the wave is completely polarized. And when m is equal to 0, that indicates a completely unpolarized wave. And when values are intermediate between those two, it indicates partial polarization. But what about quad-pol data? We would need at least 2 Stokes vectors to store all of our intensity and phase information for every channel. So because you need at least 2 sets of Stokes vectors for fully polarimetric SAR data, the Stokes vector representation is not always the most efficient way to store data. Instead, what we can use is something called the scattering matrix. Here, each of the SPQ elements represent each of the 4 transmit-receive combinations of a fully polarimetric radar. The first letter indicates the transmit polarization, and the second the receive. So typically, these are used to represent the linear horizontal and linear vertical combinations. It's interesting to note that P and Q can actually be any pair of polarizations as long as they are orthogonal. So for fully polarimetric SAR data, the Stokes vector is not the most efficient way to store data because you would need at least 2 sets of Stokes vectors. Instead, what you can use is the scattering matrix, which describes the transformation of the incident to the backscattered wave. Here, each of the SPQ elements represent each of the 4 transmit-receive combinations of a fully polarimetric radar. The first is the transmit, and the second is the receive polarization. And P and Q can be any pair of polarizations as long as they are orthogonal, and we can represent them in the scattering matrix. Each element of the scattering matrix is also a complex number containing both amplitude and phase information. There are 4 in total, and we call HH and VV our co-pol channels, and VH and VV our cross-pol. And again, what the scattering matrix is really doing is describing the transformation of the incident to the backscattered wave. So when you open a quad-pol or fully polarimetric image in something like SNAP, you'll see all these different channels, one for the real and imaginary, and one just representing the wave intensity or amplitude squared. For most natural features, though, the scattering matrix only has 3 independent parameters. HV and VH are reciprocal, and that just means that the process is the same forward as it is backwards. So what usually happens is that we average HV and VH together, and that gives us just 3 independent parameters. This is advantageous because it provides a more accurate estimate of what you would call your cross-pol returns. And this is great because returns are typically low and closer to the noise floor for these channels. So averaging improves their estimation. And when we do this averaging, it makes these elements equal, and our matrix can be said to be symmetric. But it's important to remember that when you calculate the total power, it must be the sum of all 4 elements, so we always have to multiply that cross-pol term by 2. Now, your scattering matrix will take on different forms depending on whether you're using the forward scatter alignment or back scatter alignment convention. Again, though the back scatter alignment is more commonly used, So since there are only 3 complex measurements once reciprocity has been assumed, instead of a matrix, what's called a target vector can be defined. Now K, as shown here, is the target vector in the linear coordinate form. And note that each element is a complex number still. And the superscript T reminds us that the column has been transposed. So what you can do is represent each of these elements in an RGB composite. We can also transform this data into the poly basis, which can be more efficient and easier to interpret polarimetric data. The poly basis is composed of the sum and difference of the co-pol terms and twice the cross-pol terms. Note that these are addition and subtraction of complex numbers, which helps to emphasize the difference in phase between HH and VV. Rough surface scattering is dominated by the first term, double bounce by the second, and volume and/or multiple by the third. From these target vectors, other matrices can be defined, and these can be considered second-order descriptors of the scattering matrix, which, rather than representing the channels themselves, as is the case with the scattering matrix, they characterize the statistical interrelationship between different channels, which is achieved via averaging, usually of adjacent pixels through application of a speckle filter. The covariance matrix is one of the most common, and it is generated by multiplying the target vector in the linear basis by its conjugate transpose. What that means is just applying a change in sign of the imaginary part of the complex number. And again, this characterizes the degree of similarity of the polarimetric channels. And brackets here are used to indicate that averaging has been applied, usually over multiple pixels. So there are 9 elements to the covariance matrix. 3 of these numbers are real, representing the intensity of each polarimetric channel. These are represented on the main diagonal of the matrix. There are also 6 complex values that are contained in the off-diagonal elements of the matrix. And to get the total power, we simply sum the main diagonal elements. Note again that we multiply the cross-pol term by 2. So I thought it would be interesting to show how we get those power values along the main diagonal. And again, to get the covariance matrix, we multiply a set of complex numbers by their complex conjugate. And in the case of the main diagonal elements, this gives us just the total power. I won't go into too much detail here, but this is just to show that when we multiply these 2 vectors, the result is just a rotation of the original vector so that it lies parallel with the real dimension. And then, in effect, what you have is just one magnitude value, which is equal to the length of the vector. And we know that that is equal to the wave amplitude, and if we square it, that is the total wave power. Note that we don't have any phase angle to measure here anymore. And that is how we get the power values along the main diagonal. I won't go into too much detail here about what all the other elements mean because interpreting these can be really difficult. And in fact, that's one of the reasons why we apply decompositions. I will just say, for example, though, that elements C12 and C21 are close to 0 for natural targets, though do contain some useful information in urban areas. Element C13 is also the phase difference between HH and VV, which can be useful for distinguishing between odd and even number of bounces. So it's the same process for generating the coherency matrix. We multiply the target vector in the poly basis by its conjugate transpose. And again, for polarimetric channels, this matrix characterizes their degree of similarity. So often the question is asked whether the covariance and the coherency matrices are equivalent. You can transform one into the other, and they contain the same information about correlation, phase, and intensity, but the coherency matrix does a better job at physically interpreting the scattering mechanisms from the target, and elements are more related to the geometric and physical scattering processes. But depending on what you're doing, you do have choice to use multiple different types of matrices, and some matrices are more appropriate depending on the data type that you have available. So let's talk specifically about coherent dual pole data, which we're going to be using in the next lecture. Remember that this is data for which we do have phase and intensity information. So with dual pole data, we can still use the covariance matrix representation, but we don't have everything we need to construct a full covariance matrix. But what we can do is construct a 2x2 covariance matrix, and you can do this with either co or cross-pol data. Now, let's say that you have co-pol data. We would simply follow the same process as before. We would take our target vector in the linear basis, and in this case, we have just two elements, and we multiply it by its conjugate transpose. And remember that these are complex numbers. And what we would get from that is this 2x2 matrix. And the HH and VV intensity in this case are also represented on the main diagonal. The off-diagonal elements represented in this matrix are the phase difference between HH and HV. So now that we have an idea about some of the different matrices we can use, in this final section on polarimetry, we're now going to go ahead and talk about polarimetric decompositions. Polarimetric decomposition is really just used to describe a target's scattering properties and focuses on partitioning the total power into relative contributions from different idealized scatterers. And the whole idea or goal is just to make image interpretation easier. And we can talk about two different types of decomposition methods: coherent methods, which are more appropriate for human-made or unnatural targets like buildings, and incoherent methods, which are more appropriate for natural targets. An example would be a forested area. The whole idea behind coherent decomposition is that we want to express the scattering matrix as a combination of responses from simpler canonical objects. And we do this because to directly interpret individual elements of the scattering matrix can be difficult. And this type of decomposition is ideally suited, again, for what we call coherent point or pure targets. And these are targets for which the phase is known and predictable. So an urban area would be a good example of this. Now let's have a look at incoherent decomposition methods. Because of speckle, it's necessary to characterize some targets statistically, and this cannot be done using the scattering matrix. So we need second-order descriptors like the covariance and the coherency matrix that we just went over. However, direct interpretation of these is also difficult, so we can express those as a combination of responses from simpler targets. And these decomposition methods are appropriate for natural features like forested areas. Now, there are a lot of different decomposition methods, some of which are for coherent or incoherent targets, and some of which are based on the covariance or coherency matrix, or the scattering matrix. We don't have time in this lecture to go over every one, but we will go over one example, which is the Cloud-Poitier decomposition that is based on the coherency matrix. The Cloud-Poitier decomposition is what's called an eigenvector-eigenvalue-based decomposition, And from this, we get three secondary parameters, including the entropy, anisotropy, and mean alpha angle. Entropy describes the degree of randomness of scattering, with values equal to 1 indicating a distributed target where there are multiple individual scatterers. Values of 0 indicate pure targets where there's just one scattering mechanism. And when entropy values are greater than 0.7, it can be difficult to interpret scattering mechanisms, so we use anisotropy as a complementary information source. In the figure on the right side of the slide, you'll see an example of a RadarSat-2 quad-pol image that was acquired along the coast of Canada. And what you can see is that over water, values are low, indicating that there is one dominant scattering process, whereas values over land are high, indicating multiple scattering processes in the presence of vegetation. Anisotropy indicates the relative importance between secondary and tertiary scattering mechanisms. When the values are greater than 0, a low value indicates a third scattering mechanism contributes significantly to the total power. And when the values are high, only the second contributes significantly to total power. When anisotropy values are equal to 0, contributions from the second and third scattering mechanisms are equal. So in the example on the right-hand side, again, you'll see that we have near equal contributions over land, as indicated by the color blue. Finally, the mean alpha angle is used to determine the dominant scattering mechanisms. Values range from 0 to 90 degrees, with low values from 0 to 45 degrees indicating surface or odd bounce scattering. Intermediate values around 45 degrees indicate volume or multiple scattering, and values greater than 45 degrees indicate double bounce scattering. Now, although we weren't able to cover everything today, there are many great tutorials out there that you can find more information on the things we didn't get a chance to cover. And of course, we're going to be talking in greater depth about these things in the following sessions. Here are some additional references and contributors that helps prepare this material. And I just wanted to say thank you for everyone for attending this session on SAR Polarimetry.
Hello, my name is Dr. Laura Dingle Robertson, and I work in Research and Development at Agriculture and Agri-Food Canada, AAFC, using SAR and optical satellites for mapping and monitoring agriculture in Canada. In this session, I will provide instructions on how to create intensity-derived SAR parameters from RadarSat constellation mission fully polarimetric data. Intensity of each pixel represents the proportion of microwave backscattered from that area on the ground and depends on a variety of factors: types, sizes, shapes, and orientations of the scatterers in the target area, moisture content of the target area, frequency and polarization, as well as the incidence angles of the radar beam. The pixel intensity values are often converted to a physical quantity called the backscattering coefficient, or the normalized radar cross-section, measured in decibels, dB units, with values ranging from +5 dB for very bright objects to -40 dB for very dark surfaces. Intensity-derived parameters are not concerned with phase information of complex SAR systems. They can simply be generated from the backscatter coefficient. There are several intensity parameters that can be derived in particular while using ESA's SNAP processing tool. These include total power, or intensity, called SPAN, radar vegetation index, the radar forest degradation index, biomass index, and canopy structure index, the co-pol and cross-pol ratios, HH over HV, HH over VV, and VV over VH, and all of these, the indexes and the co-pol and cross-pol ratios, integrate backscatter from different polarizations to one value. Like optical indices, these mitigate system error and noise. Assuming calibration error is the same for all polarizations, a ratio or index may mitigate the error and may mitigate some impacts of changes in incidence angles if you're using several images. Generally, generating these require fully polarimetric or quad polarimetric data with VV, HH, and VH/HV intensity. These can come from sensors like RCM or SALCOM, for example. But also newer indices and ratios are being generated with the dual polarimetric Sentinel-1 data. Total intensity or span. This is a quantity giving the total power intensity received by the 4 channels of a fully polarimetric radar system. Or if we're considering a dual polarimetric system, that would be the 2 channels of received intensity. In terms of a scattering matrix, the total power is equal to the sum of all matrix elements. And the equation for calculating span is the sum of HH plus 2HV plus VV, where HV is multiplied by 2 due to the reciprocity condition where HV equals VH. What you see in the span image here from June in Canada on the left, you have low span or low total power or intensity in bare agricultural fields represented by the red color. And this is due to the quasi-specular reflection on these bare fields of the SAR waves. The high span or dark blue areas in mixed forest and shrub areas is due to the high radar return that can be linked to what is known as volume scattering. Other intensity-derived parameters can be generated by combining the intensity channels such as HH, VV, and VH along with scaling factors in a similar way to optical imagery manipulation. In these scenarios, the combinations of the intensity channels to one value help simplify the response, but allow for quantitative and qualitative evaluations of agriculture vegetation cover, health, and growth dynamics. One such example is the Radar Vegetation Index, or RVI, and it's used to estimate vegetation conditions similar to NDVI. HV backscatter is highly impacted by vegetation. RVI is calculated as 8 times HV over the sum of HH, VV, and 2 times HV. 8 is a scaling factor because HV values are significantly lower as compared to HH and VV. As I mentioned, other indices available in SNAP include the Radar Forest Degradation Index, the Biomass Index, and the Canopy Structure Index. When you're using these, you really should try and understand the physics behind them and their associated equations to make a true assessment as to whether or not they will be useful for agricultural applications. Currently, we've only been looking at using this Radar Vegetation Index that is available through SNAP for our agricultural purposes. Here's an example of temporal RVI. Here we have 3 RVI images that were generated from RCM imagery over a site in Manitoba, Canada. The growing season in this region ranges from seeding out in May to full harvesting in August and September onwards. In these RVI images that were generated with SNAP, low values are represented by a blue color and high values are represented by red or orange color. Throughout time from July to September, we see that the values are lower and there is more blue representing lower radar vegetation index values. This is representative of the drying out of the crops and leaves dropping off the plants and harvesting that is going on throughout these months. We would expect that the most green period, or the period with the most volume scattering, would be in about July, which is representative of the majority of the yellow and orange red values we are seeing in the first image from July 19th. But you will notice there are high values of RVI in red in September. And while this could be representative of maybe strong vegetation values at that time, it could also be a reflection of a rough response from rough soils. So in particular, you'll see these red circles. And these circular fields are actually, in this area, usually potato fields. So potatoes, when they're harvested, have very deep trenches, some of which are filled with harvested potatoes. And these values have these surfaces have a very rough surface. And these values, these high RVI values, could actually be related to those rows and rough surfaces and how these have all been harvested. So it's very important when you're using indices to actually understand what's happening on the ground rather than simply trying to represent RVI, high RVI to high green values. An additional type of intensity-derived parameter are intensity ratios. These can be simple ratios that integrate the backscatter intensity from the different polarizations into one simple value. To calculate these values from fully polarimetric SAR data, you have the first cross-pol ratio of HH over HV, the second cross-pol ratio of VV over VH, and the co-pol ratio of HH over VV. Correlations have been found with simple ratios and LAI on biomass, which, as we can see in the table on the left, cereal crops of wheat, oats, and barley are negatively correlated to the cross-pol ratio of HV over HH and positively correlated to both the cross-pol HV over VV and the co-pol ratio of VV over HH. In the figure on the right, we can derive LAI maps, which are based on these correlations, and from those values, pick out the crop type for the varying values. So under the red circled fields, these are barley fields, the yellow fields represent spring wheat fields, and the blue outline fields represent oats. There are very simple steps with which to generate these intensity-derived parameters in SNAP. The following is a demonstration on what steps to take to create these parameters. We will use the RADARSAT constellation mission data, fully polarimetric quad-pol QP image from July 23rd, 2020. The 5 steps that are used to process this in SNAP are first a radiometric conversion, then the generation of the parameters, the speckle filtering, a geometric correction, and finally, you have your outputted parameters. While the parameters we'll be generating today are all intensity-based and do not require phase information, we will be using the slant range SLC product single look complex products. Each image pixel is representative by a complex, real I, and imaginary Q magnitude value. No interpolation into ground range coordinates is performed during the pre-processing for an SLC image products, and the range coordinate is given in the radar slant range rather than the ground range. So, for example, the range resolution is measured along the slant path perpendicular to the track of the sensor. The processing for all SLC products covers a single look in both the range and azimuth directions. RCM imagery is available to anyone through the Earth Observation Data Management System, EODMS. You can gain access to the data by first going and registering for a user account at EODMS. Next, you will apply for vetted user access. This is an application that is assessed by Global Affairs Canada and the Canadian Space Agency. Once access is granted, you will have the ability to access the RCM catalog. RCM does not collect continuous coverage imagery in the same manner as Sentinel-1. RCM is a Government of Canada-owned satellite constellation that's primary purpose is for the operations of Government of Canada departments. Thusly, acquisition plans are driven by Government of Canada needs. The majority of imagery collected is therefore over Canada. However, there are acquisitions that do occur over much of the other parts of the world. Once you receive your vetted user access, you can check the catalog to see if imagery has been collected over your site of interest. The first step in the data imagery processing is the radiometric conversion. SAR SLC products are complex and must be converted to intensity and phase channels. The conversion is mission-specific, and for polarimetric processing, the data must be complex. Lookup tables, LUTs, provided with the RCM SLC products are used to convert the digital number to complex real and imaginary bands. SNAP will automatically determine which kind of input product you have and what conversion needs to be applied based on the product's metadata. First, you will open the RCM image in SNAP. Start the Snap tool and be sure to unzip the RCM image. In the Snap interface, you will go to the File menu and open the product. You can click through the RCM folders until you find the manifest.sape file. You will select Advance and then select Yes. You can also drag and drop the folder directly into the Snap product window. The Product Explorer window of Snap contains like pole and cross-pol bands in the intensity and complex formats. Next, you will complete the radiometric conversion in Snap. You will go to the Radar menu, and then you will go to the Radiometric drop-down tab. You will select the Calibrate option, and the calibration window will subsequently pop up. On the I/O Parameters tab, you will make sure that your source is set to the raw RCM image and that you've named an output product and an output location for your target product. On the Processing Parameters tab, you just want to ensure that all source parameters are selected and that you're saving your output as complex output. You will run the window and it will close when completed. Next, you will generate the intensity-derived polarimetric parameters in Snap. You will first select the Radar menu once again and go to the Polarimetric dropdown. Then you will select the output of the polarimetric parameters. The Compute Polarimetric Parameters window will then open. Under the I/O Parameters tab, you will select that previously calibrated image and make sure that you've indicated where the target product should go. Under the Processing Parameters tab, this is where you're going to indicate which parameters you would like generated. You will see there are other parameters that we have not described in this session. You can also choose those as well. For today's activity, we will simply choose span, or total intensity or power, the radar vegetation index, and the co-pol and cross-pol ratios. These are intensity-derived parameters, and therefore you can apply a regular radar speckle filtering to be used. The choice of filter type and size should be related to your area of interest and what your final data is going to be used for. To generate to process the imagery and then apply a radar speckle filter, you need again to go to the Radar tab and choose the speckle filtering dropdown. You will simply be doing a single product speckle filter. Once again, the single product speckle filter window will open up. Ensure again your I/O parameters is selecting the calibrated parameters images, and you've indicated a place for your target images to go. Your source bands should be indicated as the parameters that you've generated: span, RVI, and the 3 different co-pol cross-pol ratios. Then you need to select the type of filter you want to use and your appropriate window size. The choice of a filter type is very specific to your area of interest. In our particular case, in this area of Canada, we have very large fields, and previous testing has shown that we can use very large window sizes, 9 by 9, in order to apply the speckle filtering. We also have done previous research for our areas of interest and have chosen the gamma map filter, but there are other filter types, and you should look into that for your area of interest. Once these parameters are selected, you click Run and close the window when completed. Terrain correction with the use of a digital elevation model, or DEM data, corrects the topographical distortions like foreshortening, layover, or shadowing. The range Doppler approach is one way to perform a geometric correction or terrain correction. This method needs information about the topography, as provided by a DEM, as well as the orbit satellite information to correct the topographic distortions and derive a precise geolocation for each pixel of the image. To process this, you need again to go to the radar menu and the geometric dropdown, selecting the terrain correction and then the range Doppler terrain correction method. The range Doppler terrain correction window will open, And again, under the IO parameters, you want to make sure that your source is the speckle filtered parameters and that you've indicated a place for your target output. Under the Processing Parameter tab, you will need to make sure that the choices of these options, digital elevation model, map projection, are related to your area of interest. In this scenario, we use the SRTM 1-second HGT DEM, which is available over this part of Canada, and we use a map projection of UTM Zone 14 with a WGS 1984, which is related to the area. Once you have chosen the parameters as appropriate to your AOI, you click Run and Close, and the process will be complete. And what you end up with is a geometrically speckle filtered, corrected intensity parameter image. In this scenario, the span image from an RCM July 23rd, 2020 image over Carmen, Manitoba, Canada. As I've noted before in my examples, there are many things that you can do with these parameters for monitoring agriculture. You can use these images in classifications. You can do correlation analysis with the values in relation to biomass and LAI, and you can use them in a time series for assessments of change over the land. This demonstration should help you start to explore SAR data just beyond using simple intensity or backscatter. In our next session, we will demonstrate how to derive polarimetric parameters, which consider phase from both dual polarimetric Sentinel-1 imagery and fully polarimetric RCM and SALCOM time series data.
Thank you, Laura, for a wonderful demonstration on intensity-derived parameters for agriculture monitoring. We will now transition to the question and answer session of today's training. Please enter your questions in the question and answer box, and we will get to them in the order they were received. We will post the question and answer document to the training website before the start of next week's training. Below is the contact information for Sarah and Laura, along with links to the training web pages and ARSET's Twitter handle. For those who are interested in getting a jump start with the code we will use in part 2 to process polarimetry data, we have provided missing sections of the Python code accessible by Jupyter Notebook. The code and data can be found under part 1 of the training on our website. We recommend that you attempt this before attending part 2 to better familiarize yourselves with the fully polarimetric imagery. We've also provided the solutions to the Python code in the part 2 folder, Python code, for those who might need help. Again, all of this will be covered thoroughly next week, but we wanted to offer participants the option of working with the code before next week's practical. Thank you, and we will now start with the question and answer session. Great, and it looks like we've had some really good questions coming in, so thank you for everybody who has been submitting them. We can jump right into it. Question number 1, what is the difference in the data for signals received in H and V for a same signal sent in V? And whoever answered that one, feel free to unmute and you can speak out.
Hi, so I hope that this answers the question. Hearing it again, I'm not entirely sure, but please feel free to correct me. But a strong return in the VV, meaning you transmit and receive in the linear vertical, that would indicate that your targets also have a linear vertical orientation. So an example would be a cornfield. So you would typically see a strong VV return from corn, which is also tall and aligned in that vertical direction. Conversely, a strong return in the VH, that would be indicative of multiple or volume scattering. So that's something that we typically see for objects that have a random orientation as well. So if you think about the branches and leaves and stems within a forested area, those are all randomly oriented. And so we would see a strong VH return from that type of surface.
Great, thanks, Sarah. And question 2, can a SAR sensor typically send out multiple polarizations, or do they typically only have 1 or 2? How can you tell on the data what polarization it is?
So I answered this question as well. Most sensors today have the capacity to acquire multiple different polarizations and even quad-pol data. So we use RadarSat 2 a lot in Canada, so that's the example that I gave. RadarSat 2 can acquire single pole data, dual pole data, and quad pole data. And you can task the satellite to acquire whatever data type you would like. Sentinel-1 also has the capacity to acquire quad pole data, but most of the time it operates in that dual pole mode. In order to figure out what type of polarization you're working with, though, you can refer to the metadata. It's always listed what polarization was acquired. And because you can request a specific polarization depending on the sensor, you'll always know what polarization it is. And it just takes a little bit of familiarity with working with the data. And after you've worked with the data for some time, you can also tell visually between HH versus HV, for example, depending on how much backscatter you get from the target.
Great, thanks, Sarah. Question 3, how do I calculate RVI from Sentinel-1 data for areas where HH polarization data are not available?
Okay, so I will answer that. So RVI is a vegetation index that was created using fully polarimetric data. So that would be the quad pole data that Sarah was talking about. Therefore, it's not really possible to generate RVI using Sentinel-1 dual polarimetric data. You can generate the cross-pol ratios, such as VV over VH, and you can potentially see if there's a relationship with crop types that are similar to the relations with the fully polarimetric cross-pol ratios. In the next presentation in this series, so next week, we will describe deriving the pseudopolarimetric parameters from the dual polarimetric SLC Sentinel-1 data. So that's including things such as generating Stokes vectors, degree of linear polarization, etc. So you may have more information there.
Great, thank you, Laura. And that's great. We do hope that everybody will join for next week. We have some really wonderful practicals, so please do continue through this webinar series. And question number 4, can you provide more information about the indices, example given if they will be suitable? You mentioned understanding physics, but can you provide more context information or where to look to see if it makes sense?
Yeah, hi, Sean. I answered this one. This is Heather McNairn from Agriculture Canada. So a little bit of this comes from experience. Once you get more experience working with SAR data, you'll begin to understand how waves are interacting with the target. But I just want to give it a simple example. So here I'm saying, you know, consider how do you expect the wave to scatter within the target of interest? So here we're talking about vegetation. And Sarah mentioned, for example, that these types of targets like crop canopies, they have very random oriented components. So the leaves and stalks are in all kinds of different angles and orientations. And that causes the wave that enters into those targets to either repolarize or depolarize. And we know that the cross-polarization, HV or VH, are indicative of this type of multiple scattering because of these complex structures. So given this, understanding how these waves are scattering, why they're scattering like that in a complex target like vegetation, you should be thinking about ratios or indices or other methods that are going to exploit this HV or VH intensity backscatter. So RVI is a good example of that. But if you limit yourself, you know, we want to really focus on ratios that exploit HV and VH. But if you limit yourself to ratios that do not, so you can think about a co-pol ratio like H over VV, we're not using the cross-pol component here, and you're going to miss important information about the vegetation target. There's been a lot of research published that links the intensity of HV or VH to things like crop biomass and LAI, so we know that there's a sensitivity. So this all links back to thinking about how are the waves scattering within the vegetation. Think about radar systems that are going to capture this cross-pol intensity and pick methods and ratios and other methodologies that will exploit this cross-polarization.
Wonderful, Heather. Thank you so much. And question 5, can we choose a DEM of higher resolution instead of SRTM?
Okay, so that was me. It's Laura again. Absolutely. You should consider and use the DEM that is most appropriate for your area and provides the highest resolution. So that just depends on where your area of interest is, and that you should be looking for that for your specific area of interest. You can use a downloaded and a DM that is outside of sort of the SNAP list of options. So you can, if you have a higher resolution DM, then you can use that as an external source. So be sure to look into that for your area of interest, because in some scenarios, the DEMs that are actually available on SNAP don't actually cover all areas. So you want to make sure that your area is covered and that you're using the highest resolution DEM that you can possibly use.
Great, thanks, Laura. And question 6, I would like to know which. Oh, please go ahead.
Sorry, Sean, go ahead.
Oh, I'm sorry, Heather, did you have anything you wanted to add to the answer for question?
No, I'm sorry. Go ahead and ask the question. I was going to answer before you stated the question.
Oh, okay, no problem. That's great. So question 6, I would like to know which criteria should be considered to choose the most adequate speckle filter. In the example, the gamma filter was chosen. Why this one?
Okay, so it's Heather again. If you go back to the some of the previous webinars that we delivered on radar basics, we talk a lot about filtering and different types of filters that you can choose. The most important thing here is that you choose a radar filter that respects the statistics of the radar scattering, but also suppresses or reduces the noise. So you have to choose one of these radar adaptive filters. And there are several of them available. Again, you can go back to the background material we delivered previously to take a look at them. Gamma is one that's widely used. It's a radar adaptive filter. It tends to respect or preserve edges, so field edges, for example. But it's not the only radar filter that you can choose. The second important decision on picking a filter is the size of the kernel that you use to when you're applying the filter. There's not a simple answer to that. You have to think about the filter size relative to the target or the unit of area that you want to reduce the noise. So if we think about field sizes, you want to change the size of the filter kernel to be adaptive to your field sizes. And in our experience with our research, using the largest filter sizes possible tends to produce the best results.
Wonderful. Thank you, Heather. Question 7, can we apply polarimetric parameters, ratios, RV, etc., after pre-processing of the data, like speckle filtering, terrain and radiometric correcting, and subsetting, or is it to be applied before these steps, excuse me, as told here? What could be the differences between the two results?
Okay, so that's me again, that's Laura. So we generally follow these steps that we presented here to process the data and generate these parameters, so these intensity-derived parameters. We've done completed research in the past for order of operations of pre-processing, particularly just for generating intensity or backscatter. This was for our crop classification pre-processing. So we've found that in many cases, it doesn't really make a difference in terms of the order of operations for the generation of the actual intensity or backscatter, other than we've noticed there's actually a time difference in terms of when each option is in the order. So what this could be important for is operational endeavors. And we do have a link to a paper that we could put up for people to look at, because there was a lot of testing over sites in Canada, the US, and Argentina, particularly in relation to sort of the methods of preprocessing and then the order of operations. We haven't really looked at testing it for these generation of these intensity-derived parameters, but I suspect it would be a similar aspect.
Thank you, Laura. Question number 8. How do you calculate the plant height from single-look complex data?
So this is me again, Sean, and I'm just trying to formulate my answer as we're going through these. So certainly from single look complex data, one thing that we get from that is phase information. So when this question was posed, I was originally thinking maybe the person asking the question was thinking about INSAR as the methodology. So I'll talk about that first. So if we think about phase, as Sarah was talking about, phase is about the distance or the time that it takes the signal to go from the satellite to the target, to the crop canopy in this example. And so if that time or distance changes, that tells us that the target, the height of the target is changing. So INSAR is used for these types of things. So changes in deformation of the Earth's surface, for example. So you can, sometimes we think, could we use INSAR to look at how crops are growing? So we know as crops grow, they get higher, and the distance from the radar antenna to the top of the canopy changes. This can be a bit tricky though, because we have this issue about decorrelation over time. So you can think about, when the crops are growing, it's not just the height that's changing, but how the leaves are oriented can change, because we can have wind occurring, or the crop canopy is just filling out. And so we can get this temporal decorrelation. So using INSAR to measure crop height can be a bit tricky unless we have good correlation, phase correlation over time. If you think about big canopies, and one type of canopy we're looking at are bananas. So these have really big leaves, and so it's possible that we won't see as much temporal decorrelation over time, and we might be able to use this phase information. Other than that, if you talk about intensity from SLC data, so SLC means we get intensity and phase. There's been quite a bit of work looking at modeling crop height or biomass or LAI using semi-empirical models, something like the water cloud model, for example. But in those cases, we're by and large just exploiting the intensity.
Great, thank you, Heather. Question number 9, what are the best vegetation indices for crops we can estimate from Sentinel-1?
Okay, so this is me again. We have yet to really start looking at sort of these vegetation indices derived from Sentinel-1 in our own research, but obviously have started to look at vegetation indices derived from fully polarimetric data, including such data as RadarSat-2 and RCM data. And as I've mentioned in the past, we can look and provide links to papers on that research as well. For the Sentinel-1 data, I think it would be best if someone was really interested in trying to understand vegetation indices, is to start looking in the literature, and then of course testing in the area of interest, because of course that's kind of what we do in research, is just try to figure out what works well and where and when. So for that, I think we'd have to go with that answer.
Thank you, Laura. Question 10, please tell me how to download microwave remote sensing images for the above analysis.
Okay, so this is again me, and so for the RCM data that we used in this research, or this presentation, sorry. So I believe our site will have links to the actual imagery, so you can practice based on what you saw here. However, if you want to access the actual RCM catalog, so this is everything that's been collected from RCM, you can do this. You go to what we call the Earth Observation Data Management website. We can provide that link, and you will register for an account. So you would just go on there, and there's a spot which to register for an account, and you would register for an account. Then to access RCM, you need to apply for vetted user access. And so there is a link on EODMS, and it just brings you to a form that you complete fully with your information. And then that is actually reviewed and vetted by the Global Affairs Canada and the Canadian Space Agency. And then once you're vetted, you will gain access to the RCM catalog, and you'll be able to search up what data is available where. Like I said in the presentation, a lot of the data collected for RCM is collected over Canada because they are operational satellites. They are meant for the operations of the Government of Canada. But there are other areas of the world where there is data collected, so you may find that there are data over your particular area of interest. So that's the way you can get access to RCM.
Laura, thank you so much. That's great. And we did add a link here to the web page for this training. You can access the RCM data that is being shown in both the first two parts of this training. So we do encourage you to go to the link that we've provided, and you can access the data that's being used specific to this training. But we will also go back and add the link that Laura just mentioned for the EODMS site. We will add that when we clean up this document and before we post it next Tuesday for part 2 of the training. So thank you. Question 11, how do I do corrections in the tiles to make it homogeneous while doing mosaic?
So I answered this as best I could. I suspect this might be a really great question for our ESA colleagues who will be presenting further along in this series. So I'm hoping that we can keep this question and maybe ask them as well, because I'm not exactly 100% sure on how to do this. But yeah, I think that'll be a good question for ESA.
Great, sounds good. Thank you, Laura. Question 12, what might be some of the good resources / lists to study SAR-based indices?
Sorry, that was me. Laura, Heather, and I, and Dr. Gopika Suresh, we work collaboratively to keep a running list of multiple SAR training resources as part of our work as the Sisters of SAR on Twitter. So I've just put a link to our website, and you can go ahead and check it out. There are a ton of different resources that are available nowadays. So there's tons of stuff online you can find.
Great, thanks, Sarah. Question 13, does RVI correlate with NDVI? Where does it fail?
So this is Heather again. We've looked at this quite a bit in our research group, and the strength of the correlation between RVI and NDVI has varied. So we have noted that for some crops, the correlations are pretty strong, and for other crops, they're not as well correlated. So the question is, why would some crops work better than others? So again, think about the fact that RVI uses two co-pol linear polarizations, HH and BB. And we know in particular, HH is not a particularly useful polarization for crops. There are some crops like forage crops, so you can think about pastures and alfalfa. There's a better correlation with HH for those crops. But other field crops like corn, soybeans, wheat, these types of crops, the HH backscatter is not very useful and can often confuse the situation. So RVI uses HH, and so this is why sometimes we get better correlations with some crops than others. And I just added in the comments that we are in the process of developing a radar vegetation index, our team is, others are as well. And really we're focusing on the polarimetric parameters that are sensitive to volume scattering. So recall what Sarah's talking about, think about how the waves are scattering in the target. So these vegetation indices are really exploiting those parameters like the cross-pol intensity we talked about, parameters like entropy, and even some of the decomposition parameters like volume scattering.
Great, thanks, Heather. Question 14, is there any non-negligible impact of wind and other weather conditions over intensity and polarization returns? And if so, how can we eliminate them?
So I started to answer this, but I think maybe Heather might have a better idea for agricultural areas, but I just wanted to add here that these effects are really dependent on the target. So hard targets, specifically like a building, it wouldn't be affected by the wind or weather conditions, but vegetation can be. Wind can actually change the orientation of the vegetation, and that can in turn affect the backscatter that you receive at the sensor. If your canopy is wet as well, this can also affect your data, and it can be difficult to sort of remove the effects.
Great. Thank you, Sarah. Question 15. The RVI formula uses sigma naught data, but the calibration in the example output complex numbers. Is calibration to sigma enough not required?
I'm not entirely sure that I understand this question either, so please feel free to correct me, but I was just going to say that sigma naught is the radar reflectivity per unit area on the ground. So it reflects how the data are calibrated, and that's sort of different how we express them in terms of phase and intensity, which is with complex numbers.
Thank you, Sarah. Question 16. Can those parameters be calculated with RadarSat 2?
I can just jump on here. Yes, RadarSat 2 is fully polarimetric data, so those parameters can actually be calculated with RadarSat 2 because you have access to HH, HV, VH, and VV.
Thank you, Sarah. Question 17. How can cross-pol power and volume scattering power be analyzed over agricultural fields?
Sure, I can try to answer this one. So again, think back to crop canopies and how different they are in their structures. So if you think about a corn canopy or a rice canopy or a forage canopy, the size and orientation of the leaves and stalks are quite different, and that's going to create different amounts of volume scattering, whether that's measured through the intensity of a cross-pol channel like HV or VH, or whether that we do that through volume scattering that we can get from some of these decompositions. And you should note that the cross-pol power and volume scattering are often highly correlated, so you can measure this amount, the differences in volume scattering from these different targets using really either of those parameters. So we can use this. These are both good parameters to complete classification. So in fact, the cross-pol power is the most important polarization in order to be able to classify different crop types. We use that a lot in agricultural classification. If you're looking for other parameters like biomass or LAI, this is usually done through some sort of modeling. The water cloud model is one that many have used, including my team, and in that case, we're primarily looking at things like volume scattering or cross-pol scattering, and we're creating a model between field measured data and the amount of scattering, whether it's measured through cross-pol or volume scattering.
Once again, that's Heather McNairn from Agriculture and Agri-Food Canada. Thank you, Heather. Question 18. Looks like this participant is seeking clarification. When we talk about phase data, are we referring to the phase difference between the emitted wavelength and the received one? I just want to confirm if I got it right or not. Thank you.
Hi, this is Sarah Banks again. So the phase difference that we're talking about would be the phase difference between HH and VV, so two separate polarizations. So you can imagine if we transmit H and V at the same time, the phase difference we're talking about would be the time delay between when we receive those back at the sensor.
Great. Question 19. As far as I know, a 35 to 45 degrees incidence angle is mostly suitable for crop monitoring with the SAR dataset. A bit more explanation on that will be helpful. Thanks.
Sean, it's Heather McNairn again. I'll try to answer this one. I don't think it's as straightforward as a particular incidence angle range. I always frame it this way: is that We have to think about the frequency of the radar as well, whether it's X-band, C-band, or L-band. And we have to think about the growth stage. So are we talking about early in the cropping season, or maybe the crop is more advanced? So pick an incidence angle that you think is going to provide, good interaction within the canopy itself. We want to minimize the amount of contributions typically coming from the soil. So that's why we don't want these really steep incidence angles. But we also want enough penetration into the target so that we get all of this volume scattering that's happening within the target. So I think the person who asked this question is in the ballpark. I think we want these shallower angles that provide a scattering within the volume, but think about the size of your canopy, what the crop type is, the growth stage, as well as the frequency. So pick an angle where we have penetration into the canopy, deep enough into the canopy to interact with the canopy structure, but not penetrating so far that we're getting these contributions from the soil.
Thanks, Heather. Question 20, is polarization only horizontal and vertical? Can it be at an angle?
Yes, it can be at an angle, but usually we just transmit and receive in the linear horizontal and linear vertical. Those are the most common polarizations that are used.
Thanks, Sarah. Question 21, can SAR data be used in deriving optical image vegetation index?
Okay, so that was me. So as Heather mentioned, we are looking at working on a SAR vegetation indice that's looking or being derived from fully polarimetric data, and in particularly those parameters relating to the volume scattering. And we're looking at this in relationship to sort of that typical NDVI, normalized difference vegetation index, that is an optical image vegetation index, so as Heather mentioned. So again, we can try and provide links to some papers on that, and there are others, as Heather mentioned, that we are also looking at this kind of research as well. So using SAR data and deriving a vegetation index and relating those to optically derived vegetation indices.
Thank you, Laura. Question 22, the sensor ALOS has ceased to operate since 2011. How do we currently obtain polarimetric datasets?
So I answered this again. I was taking it as an interest in L-band polarimetric data. So ALOS2, Pulsar2, and I believe ALOS4, but I would say go to the JAXA website to double check. Well, ALOS2 and Pulsar2 offers fully polarimetric data. They are available through JAXA. I imagine if you go to JAXA's website and check that out, there might be a way in which to acquire that fully polarimetric L-band data. As well, I believe there's fully polarimetric options from the SAOCOM data, and I believe our ESA colleagues just mentioned that it's SAOCOM, some of the SAOCOM data will be available through their site, so we might want to double check with ESA on sort of access to the SAOCOM L-band data. And as well, NISAR, which is expected to launch in 2023, is supposed to have a fully polarimetric option, although it should be only available over certain areas from my understanding. So that was my understanding of what they were talking about in terms of L-band data, polarimetric data.
Terrific. Question 23, to what extent can RVI be compared with NDVI? Is data fusion possible?
Yeah, so I answered that question. It's Heather again. So we answered most of that under question 13, but I will add that our team at Agriculture Canada is creating a radar vegetation index. We've mentioned that a few times. And what we're trying to do is not just create a radar vegetation index, but to calibrate it to NDVI. So that if you track vegetation development over the growing season and you have a vegetation index curve, any point on that curve can come from optical or radar data. So bear in mind that a lot of user communities are well embedded in NDVI. So they're doing regional, national, global operations using NDVI. So we have to make sure that radar is fitting into that feature space. And so the user is not going to really care whether the vegetation condition is being described by a radar sensor or by an optical sensor. The most important thing is that the crop development is going to be well described.
Thanks, Heather. Question 24, may we assume that different crops generate different signal responses based on SAR, that we may further use to recognize different crops?
So this was me, and completely. This is one of the areas that we are fully interested in, and we've done a lot of research on, and over years and decades at AAFC in terms of the SAR response over different crop types. So when you're thinking about SAR and the interaction of the waves, you should be thinking about the actual crop types and the form of the specific crop types, how they're planted, how they grow, and as well, you should be thinking about the frequency of the SAR wave. So is it a small SAR wave, an X-band SAR wave? Is it a little bit bigger at C-band, or is it a longer SAR wave as an L-band? And how do those waves interact with those crop types? In terms of where they are at their phenology. So these interactions all change, obviously, as the crop is planted, it emerges, it may have small amount of leaves, it may have a very sort of tall linear structure with a lot of exposure to soil around it. It changes as it flowers, or as the flowers then develop into pods or seeds, and then subsequently these crop types are ripening and harvesting. So for sure, different crop types do generate different signal responses. And again, I don't like to point to the literature, but there is a lot of different literature over different crop types. So sort of typical wheat, soybean, canola type crops, or rice, vegetables, and there's a lot of different research out there on how the SAR signal actually interacts with different crop types and what you should expect in terms of the response.
Thank you, Laura. Question 25. What are the critical factors to combine ascending and descending modes? What is an effective way to do so?
Okay, so it's Heather. I tried to answer this one as well. So we think about ascending and descending. The two differences that come to mind for me immediately is time of day. So one it will be usually a morning acquisition, one will be sort of a late day or evening acquisition. So there's a time of day difference. So you have to think about that. So some things in the target can change diurnally. You can think about the amount of water in vegetation. Sometimes there's a diurnal effect. Certainly soil moisture can change over that 12-hour period as well. So there's a time of day impact. So just think about the target. Is that going to change over a 12-hour period? The second difference between ascending and descending is the look direction. So that's the direction. It's not incidence angle. It's the direction that the beam sent from the radar antenna and the target. So it's the angle at which the radar is looking at the target. And if you have a target that doesn't have any structure in it, this probably won't be an issue. So think about a pasture field. There's not really any structure or periodic structure in that, so probably not an issue. But think about a situation where you have crops that are growing in rows. So corn, for example, or wheat, where we have a specific orientation of these rows, or if we're tilling a field and we have furrows in the field. Or even seeding. Sometimes we seed in these seed beds that have an orientation. So now you can think about the look angle between the radar antenna and the target is going to change because we're looking at it at a different angle, and that may or may not impact the radar scattering. So I think it's important to think about those things and what impact that might have. For crop classification, we frequently use ascending and descending. Keeping in mind about these diurnal effects. So in northern latitudes, we have a lot of dew that forms on the crop over the cooler overnight time period, and we have early morning dew. So we do tend to like to have acquisitions in the evening. But the temporal domain is really important. So if you combine ascending and descending, you're trading off a little bit about this dew effect to having a really denser coverage of acquisitions. So for crop classification, we've combined both ascending and descending, and we don't worry so much about those differences. Biophysical modeling is different though. If you want to estimate things like biomass, leaf area index, or soil moisture, you really have to pay attention to these differences, both in terms of how the target is changing, dew effects, freeze-thaw effects, moisture effects, and the, what difference this difference in look angle might bring to the radar scattering.
Okay, thanks, Heather. Question 26. What is the effect of water vapor in the air on the polarization of the electromagnetic waves?
It's Heather. I don't think I'm a good expert on this. The water vapor in the air is not generally something in radar at the wavelengths that we're talking about that we're really concerned about. If we have large enough droplets, like during rain events, then that can cause scattering, even at X and C band, for example. So, larger water particles that happen during rain events can affect the scattering of the radar, but water vapor, I think those particles are much smaller. The one thing I'll mention is that there's this, there's an effect from the ionosphere on especially L-band transmissions, and so you get this slight change in polarization at L-band, but this is in the higher ionosphere, and this slight change in transmission at L-band due to this ionospheric impact, this is usually calibrated for with the SAR radar providers.
Great. And question 27, can SNAP be used to monitor carbon sequestration?
Hi, this is Sarah. So there's quite a bit of research on this for estimating above ground biomass. And so that would be an indicator of carbon using SAR. And that's especially with longer wavelength L and P band data. And that's because they're able to effectively penetrate into the canopy, providing information on its structure. These data aren't widely available, though. You can find some archive data through JAXA, some L-band archive data, and there's new missions coming up called Biomass and NISAR, which will provide longer wavelength L and P band data that will be free and open. So one thing you can do to monitor carbon sequestration is build an empirical model if you have the field data to do so. And you can do this in SNAP. You can process the data and then kind of export the values where you've taken coincident field measurements. Another thing you can do is measure height from SAR, and that would be the height of vegetation, and use that as an input to an allometric equation. And something that you can do in SNAP is do something called INSAR, and that will give you the height of some canopies. And the effectiveness with which this works will really depend on a number of different parameters, like Heather was mentioning. You have to think about the wavelength. So if you're trying to measure the height of the canopy, use something like X band, which doesn't penetrate very deep into the canopy, but yeah, it's something that's definitely possible with SAR.
Great, thanks, Sarah. Question 28. How do we choose between gamma and sigma transformation?
Okay, so I answer this. So typically in agriculture applications, we utilize the sigma naught conversion because it's understandable in relation to the ground. So it's a measure of the it's a measure in relation to the unit area on the ground. From our understanding, gamma naught's typically more used for calibration, as the range cell is equally distanced to the satellite, so both the near and far range are equally bright. There may be instances where it's useful to use a gamma naught transformation, but typically we in our SAR applications for agriculture, we have been utilizing a sigma naught transformation.
Thanks, Laura. Question 29. Does SNAP only work with full granule/tiles as the initial input? Is there any way to take advantage of COG partial reads to read and process only a subset of a Sentinel-1 granule/tile?
So I hope I'm understanding this question right, but actually next week in the trainings next week, we will be describing how to minimize the amount of a Sentinel-1 image that you need to use for deriving the pseudopolarimetric parameters. So that's including reducing the data to specific subswaths of an interferometric wide swath image. So there's 3 subswaths, and also to minimize to actual individual bursts within an individual subswath. So we do show next week on how to actually do that type of processing, because the images are, Sentinel-1 images are really quite large, and they do take a long time to process if you're trying to use the full image, obviously.
Yeah, thank you so much. And please do join us next week, where Laura will continue with this practical and demonstrate this. So please, we hope to see you next Tuesday. Question 30, can these processes, pre-processing, be implemented in Google Earth Engine?
I answered that, and I think the short answer is it depends on what you want to do. Google Earth Engine currently, as far as I know, only provides the ground range detected data. And as I mentioned in my presentation, that you do not have phase information with that. So to do a lot of this stuff that we're talking about, you need to actually take the data outside of Earth Engine, or use Earth Engine's cloud computing platform, other resources where you have that full phase information.
Thanks, Sarah. Question 31, is the biomass index accurate if data comes from a sensor with a short wavelength, example given Sentinel-1 with a 5 centimeter wavelength?
So it's Heather, I answered this one. So to be fully candid with you, the only vegetation index within SNAP that we've worked on, our team, is RVI. So I'm just going to limit my comments to RVI. But with RVI, we've certainly evaluated its use using C-band SAR data, both RadarSat and Sentinel-1. But as a general comment, you really have to always go back to that size of the wavelength, the wavelength or the frequency of the transmitted wave, and think about how that size relates to the size of the canopy. For example, the total biomass. And we know that canopies have different amounts of biomass. So if you look at one crop type to another crop type, the amount of biomass is different. And we know that the biomass changes over the season. So from the beginning, the middle to the end of the season. And so it's a pretty complicated target we're looking at, variations in biomass over time and over space. And in that case, I think the biggest dividends, the most advancement that we will see in measuring biomass for crops will be when we start to integrate radar from different frequencies.
Thanks, Heather. Question 32, how can we deal with the biomass saturation issues, particularly with Sentinel-1 data?
So I answered this one as well, and there really is no simple answer to this, or there's no immediate solution. Again, it gets back to what I was just stating. There's just a fundamental physics behind how far these waves can penetrate into a target when we look at the size of the transmitted wave to the size of the canopy. So C-band will only get so far into those canopies, and as the canopies grow over the season, we get this saturation effect. And really, again, our solution is to look at multi-frequency radar, and I think someone just mentioned NISAR, which will be coming up shortly. And so I think this is going to be a really great opportunity to integrate sensors like NISAR with Sentinel-1, for example, and we are going to see big dividends, and that will help address some of these saturation issues. I'll just add, however, that we often think about longer wavelengths being better, and that's not necessarily true. We want, as I said before, we want the wave to penetrate into the crop canopy, but not through the crop canopy to the soil. And so that's why, even with the launch of NISAR, which will have L-band, this will be really great for big biomass crops. It may be that frequency or that wavelength is too big for smaller biomass crops. So it's really the integration of L and C-band where we're going to see the biggest advancements.
Thanks, Heather. Question 33, There are some negative pixels in the aster DEM. How do you remove them?
Hi, I answered that question. One solution you might want to think about is whether you can store the DEM locally. If then you can edit yourself manually and then point to that new edited version when you're using Snap. But I'm not entirely sure how that DEM has been edited. So it might be worthwhile to check and see if those negative values have actually already been removed in the version that Snap is pointing to.
Great, thanks, Sarah. Question 34. In the Southeast Asian region, paddy and jute are the most cultivated crops. On both, the field properties change from time to time, and with that, the dielectric properties change too. So how does that impact RBI?
Okay, it's Heather. So let me try to answer that question as well. So if we think about RVI, for example, RVI is capturing the total intensity, that the total amount of energy that's being scattered by the target. So the total amount of energy will be due to many different things, including the amount of biomass, the structure of the crops, and the water or the dielectric properties of the canopy itself, as well as the soil. So you can think about RVI as sort of capturing all of those. And so a metric like RVI or an index like RVI, it's going to be difficult to tease out what contribution is coming from changes in water and how much is coming from changes in the structure itself. There are other methods. We didn't talk about them in this lecture, but I mentioned before the water cloud model or other semi-empirical models. And in those cases, you can integrate, in those models, you can integrate both sort of the intensity or the response that's coming from changes in the dielectric of the canopy, as well as changes in things like biomass. So we've done that in some of our publications where we've derived, for example, the amount of water in the vegetation as well as the amount of biomass using these semi-empirical models, because those models are capturing both the changes in water as well as changes in biomass. So I think I would move away from RVI and look at some of these other modeling approaches.
Thanks, Heather. Question 35. Is the RCM data commercial or is it also open access?
Okay, so I answered that. So the RCM satellites, they're fully owned by the Government of Canada, but there is open access to that data through the process I described above and in the presentation. But that being said, the data collection is programmed mostly over Canada because these are operational satellites. They feed the Government of Canada departments for our operational endeavors, whether it's our annual crop applications for crop mapping or for our monitoring of our marine and other terrestrial areas. But as I also mentioned, there are imagery being acquired over other areas of the world. So if you follow the procedure to get your vetted user access, you can check the catalog to see what is available. But keep in mind, the actual acquisition plan is dictated by the Government of Canada departments.
Thank you, Laura. Question 36. In the Philippines, croplands are very small. The majority of the farmers have less than 1 hectare. Do you think polarization or any software manipulation can help determine different indices and crop classification with such very small area against the hardware resolution limitation of the SAR satellites?
So this has been a very interesting question that we've been thinking about a lot ourselves in our research. We often find that these very small crop areas are in need of a higher spatial resolution imagery, which we have access to ourselves. But there are other options that we think that will help with crop classifications in these types of areas, such as these polarimetric parameters, or using multi-frequency SAR, which both Heather and I believe Sarah have talked about, along with classifiers. So you have to think about the classifier you're using if you're trying to do a crop classification that will take into account sort of these very complex cropping systems, these small areas, these dual intercropping type agriculture systems, these long-term temporal periods in which crops are planted or when they're being harvested. So we're looking at particularly methods like deep learning methodologies such as neural networks, artificial intelligence, and we have been looking in areas in the world that have very complex cropping system with small fields, and we're finding better classification results when we're using the polarimetric parameters and when we're including things like multi-frequency data in a classifier that can handle the complexity of the situation.
Great, thank you, Laura. And looking at the time, we're almost at the 30 mark. So we do want to respect the time and end as we stated that we would. But I first want to thank everybody for joining today. For all the participants, wherever you're joining from, we hope you got a lot out of the first part of this training, and we hope you'll join us next week, next Tuesday, for part 2 of the training, where we will continue with today's practical. And we also want to thank Sarah Banks from Environment and Climate Change Canada, as well as Laura Dingle Robertson from Agriculture and Agri-Food Canada, and finally, Heather McNairn from the Agriculture and Agri-Food Canada for joining us today and providing such amazing presentations and doing such a thorough job in answering your questions. So thank you for them. And we will, for those questions that we were not able to get to, we know that there's still a handful left. We will answer them and put this on the website, and that will be accessible before next Tuesday. So for those that did not get their question answered, please do go to the website before next Tuesday to look for that. But thank you everybody again, and we look forward to seeing you next Tuesday. Thank you.